Hello everyone. Today, Ziling and me will introduce an article here, The Physics Behind Musical Instruments, a Tang of Science. The author of this article has visited the Haus der Musik, Sound Museum in Vienna. It is an amazing place where visitors can compose their own music and even conduct the famous Vienna Philharmonic Orchestra. However, the most impressive part for the author was the instrument's exhibition. By standing inside a giant's mouthpiece for wind instruments or giant hollow percussion body, one could experience firsthand how music is created. And yes, it has everything to do with physics and science. Sound is created when an object vibrates. These vibrations cause the particles in the air around the object to vibrate too. The particles bump into their neighbors, setting them into vibrating motion and allowing the vibration to travel further. For this reason, sound is often defined as vibrations that travel through air and are detected by a human's animal's ear. However, the medium does not necessarily have to be air. For example, where ears pick up vibrations transported through water. In physics, vibrations are commonly described as waves. What makes musical instruments special is that they create standing waves instead of random vibrations. In a standing wave, some points, the notes, remain fixed, while the rest of the wave vibrates with maximum amplitude. That is, the highest and the lowest points of the wave. It is these standing waves that we experience as beautiful harmonic tones. Irregular, random waves that are not standing are heard as noise. The properties of the vibrations standing wave tell us how we experience the tone. One important property is frequency, which describes how many waves pass one point during a specific time. The larger the frequency, the higher pitch the tone we hear. Conversely, the smaller the frequency, the lower the tone sounds. Another key point is amplitude, the height from the highest to the lowest point of the wave. The larger the amplitude, the louder the tone. A smaller amplitude produces a softer tone. Musical instruments create vibrations in three different ways. Percussion instruments, such as drums or bells, have a hollow body. When struck with sticks, hands, or other objects, this hollow body starts vibrating and produces the tone we hear. Wind instruments include brass instruments like trumpets and saxophones, as well as woodwind instruments like flutes. They all have a mouthpiece and a hollow tube. When the player blows into the mouthpiece, the air column inside the tube is set into vibration, and the tone is produced. String instruments work through the vibration of their tension strings. The vibrating motion can be started in different ways. The strings can be plucked, as in guitars or harps, bowed, as in violins or cellos, or struck, as in pianos. In conclusion, the physics behind musical instruments is both elegant and fundamental. All music begins with vibration that form standing waves. Frequency determines pitch, amplitude determines loudness, and the three families of instruments, percussion, wind, and string, excite and amplify these waves in their own unique ways. Next, Ziling will connect the article with our learning in lecture. Let's welcome.
Now that Lily has summarized the article, I'd like to comment on it by connecting its ideas to what we learned in our lectures on sound and musical instruments, specifically Lecture 16. The article talks about how instruments produce music, but it doesn't deeply explain what sound actually is. From our lecture, we know that sound is a mechanical wave. It needs a medium like air, water, or a solid to travel, and it cannot propagate in a vacuum. The speed depends on the density and stiffness of the medium, and in air at 25 degrees Celsius, it travels at about 340 meters per second. This is the foundation that makes everything in the article work. Without a medium, no instrument would produce audible music. The article describes how guitars and violins produce sound through vibrating strings, but our lecture gives the exact physics. The fundamental frequency of a vibrating chord follows the formula. This means three things control the pitch: length, longer string, lower frequency. That's why a bass guitar is bigger than a violin. Tension, tighter string means higher frequency. That's why guitarists tune their strings. Mass density, heavier string means lower frequency. That's why the low E string on the guitar is thicker than the high string. The article mentions tuning and string thickness, but our lecture explains why it works through standing wave physics. The article groups all wind instruments together, but our lecture makes an important distinction the article misses. Flutes and clarinets behave very differently, even though they look similar. A flute is open at both ends, so its fundamental frequency is V divided by 2L, and it produces all harmonics like F1, double F1, triple F1, and 4F1. A clarinet is closed at one end, so its fundamental is F1 equals V divided by 4L, meaning a clarinet of the same length plays an octave lower than a flute. It also only produces odd harmonic like F1, triple F1, and 5F1. This is why a clarinet and flute sound completely different even when playing the same note, and this is something not only physics can explain. The article uses words like pitch and loudness casually, but in physics, these have precise meanings. Pitch means frequency, higher frequency means a sharper, higher note. Loudness means amplitude. Bigger amplitude means louder sound, measured in decibels. From the lecture's note frequency table on page 8, we can see that middle C is 261.6 Hz and the eighth above it is 440 Hz. These are the exact frequency at which strings or air columns must vibrate to produce these notes. One thing the article doesn't cover well is electric instruments, which our lecture explains beautifully through Faraday's law of electromagnetic induction. In an electric guitar, a magnet in the pickup magnetizes the steel string. When the string vibrates, it creates a change in magnetic field, which induces an electric current in a coil around the magnet. That current is amplified and sent to a speaker, where the process reverses. The current pushes a coin back and forth to recreate a sound wave. So, an electric guitar is really a beautiful application of three physics concepts: standing waves on string, electromagnetic induction, and mechanical wave generation. In summary, the article gives a nice general overview of how instruments make music, but our lecture provides the quantitative physics behind it, the wave equations, the standing wave conditions, and the electromagnetic principles that turn vibrations into the music we enjoy. Thank you for watching and welcome for questions.